Hello, welcome to section 1.4 of the M132 course at AOU, Introduction to Linear Algebra. In this section, we will look at the inverse of a matrix. We will consider two different cases. One is for a matrix that is 3 by 3 or higher, and another one is for the case when the matrix is a 2 by 2. To begin with, we will look at any matrix. N by n matrix, which is a square matrix, is said to be invertible or has an inverse if there exists an n by n matrix such that a times b is equal to b times a is equal to I. In other words, when multiplying a and b together, if we obtain the identity matrix, that means that a and b are inverse of each other. In other words, b is inverse of a, or a is inverse of b. This is the condition for inverse. The matrix B can be denoted as a minus 1, a to the power minus 1, and is called the inverse of a. If there is no such matrix B, then a is called singular. Otherwise, a is called non-singular. So if it is non-singular, another term for it is invertible, and another term for singular is non-invertible. What are the properties of the inverse of a square matrix? The inverse of a matrix is unique. Number two, if A and B are non-singular matrices, non-singular it means invertible matrices, then A minus 1 is non-singular, and A minus 1 is equal to A. In other words, the inverse of the matrix, if we perform the inverse of the inverse, we obtain the original matrix. The transpose of the matrix is non-singular, and A transpose, the inverse of A transpose, is as if we're doing the inverse transpose. AB is non-singular. If AB is non-singular, then the inverse of A times B is equal to B minus 1 times A minus 1, which means it's equal to the inverse of B times the inverse of A. This is worth remembering. The last one is if A is non-singular and a to the power n, we want to take its inverse, then it is the same as taking the inverse and raising it to the power n. Now, how do we compute or find the inverse of a matrix that is 3 by 3 or higher? To do that, first we form the n by 2n matrix, A slash in. In other words, we append to the matrix A the identity matrix I of the same size. Number two, we transfer the matrix to the row reduced row echelon form. Okay, and then once we do that, we have two possibilities. Number one, if we obtain I on the left side, A minus 1 on the right side, it means that the job has been done and matrix A is invertible, non-singular. If we obtain C, matrix C, which is different than the identity on the left side, it means that C has a 0 row, and the conclusion is that A is singular and A is non-invertible. Now let's look at an example. If we have the matrix A, which is given below here, matrix A is a square matrix. It's a 3 by 3 matrix that we have to find its inverse. We follow the rules that have been discussed in the previous slide. Mainly, we, as stated here, we append A, we add to A the identity matrix as shown below here. And to obtain the new augmented matrix. The new augmented matrix is a 3 by 6 matrix. And then we do the row reduction operations until we obtain the identity on left side and A minus 1 is on the right hand side. How we do that is we've done this before, just we've done as if we did the elimination before. We transform these two into zeros, and this is done by R2 minus 2R1 in R2 and R3 minus 4R1 in R3. We get the matrix on the right hand side, the augmented matrix here, where we have zeros now here. Then we change this one to a 0. How we do that? By the following operation: minus 2R2 plus R3 into R3. This will change it to the way it is. It becomes upper triangular. Then we change this to a plus 1. Change it to plus 1 by multiplying the last row, row 3, by minus 1. And this will change it as you see here. Then what we have to do, go back and look at every column here. The first column here, we have a 1 here, which is called the pivot. And these two are zeros, so that's okay. We can leave it the way it is. We come back to the second row, the second column. We have 1 here, we have 0 here and 0 here, which is acceptable. We leave it as it is. Lastly, we look at the third column. We have 1 here, but we have a minus 2 and a 7 here. What we have to do is change this to a 0 and this to a 0 so that this becomes an identity matrix. And by doing so, this would be the last operation that we do. This becomes the inverse of the matrix. How we accomplish this? By the following two operations: R1 plus 2R3 in R1, R2 minus 7R3 in R2. In other words, we use the last row as our reference. Once we do that, we obtain the identity matrix on the left side and the inverse matrix on the right hand side. And A minus 1 is 1, 4, minus 2, minus 2, minus 13, 7, 0, 2, minus 1. This completes the task. Another way of doing the inverse of the matrix, this is specific only for a 2 by 2 matrix. Note that the previous method, where we append the matrix by the identity matrix or augmented by the identity matrix, can be applied to the 2 by 2 as well. But this formula cannot be applied to the 3 by 3 and 4 by 4 matrices. This is only specific to 2 by 2 matrices. And the formula is as follows. If A is a 2 by 2 matrix that has elements A, B, C, D, then A minus 1 is equal to 1 over AD minus BC times. We exchange the first and fourth elements, exchange their position, and we change the sign of the second and third elements, and they stay where they are. This is how we find the inverse of a 2 by 2 matrix. As an example, if A is a 2 by 2 matrix with elements 2, 1, 6, 4 as seen here, then A minus 1, applying the formula, is equal to 1 over 2 times 4 minus 6 times 1. Then the 4 is exchanged with the 2 here, and the signs of 1 and 6 are modified to become negative. Then the matrix becomes here, this is 8 minus 6 is 1 over 2, 4 minus 1 minus 6, 2. Then we multiply each element by the 2. So we have 4 divided by 2 is 2, minus 1 divided by 2 is 0.5, minus 6 divided by 2 is minus 3, and 2 divided by 2 is 1. We can always check our work by multiplying the original matrix by its own inverse. And this produces the identity. Sure enough, we can see that when we do the check, if we multiply the two matrices, we start off by, as we did before in the previous section, 2 times 2 minus plus 1 times minus 3, this is equal to 1. Then we take this row times this column to obtain a 0, then this row times this column to obtain a 0 here, and lastly this row times this column to obtain a 1, which is the identity 2 by 2 identity matrix. This completes section 1.4 of chapter 1. Good luck.